Okay, 4.2, carry on exactly where we were, is our introduction to continuous probability distribution. So a continuous probability distribution, the word continuous we learned last unit, as an aside to what discrete means. Discrete means it has to be an integer value, okay, a whole number value, the number of oranges in your fridge, something like that. Continuous means it can take on any value. And the fact that we're joining all of these red lines or curves together means that whatever's on the horizontal axis, it's just not limited to integers, right? It can be at any value, so you can actually join the curve to show the trend of what's occurring. So on the first couple pages of 4.2, we're just sort of introducing or reintroducing, because if you read through 4.1, you've been introduced to a couple of these, some of the main distributions that we're going to encounter as we move forward. Okay, and the number one is the normal distribution, and it is in fact going to be the focus of the rest of this unit. We are just going to base it on a normal distribution. So the two ones that you sort of have to look at the most are what's called a uniform distribution and a normal distribution. A uniform distribution has attached to it equal probability of everything happening. So the best sort of scenario that we look at for a uniform distribution is the idea if you had a dice and you were rolling it. Okay, your options would be 1 through 6 with a probability of 1/6. Remember, these distributions are what we learned in the last lesson. X, random variables on the horizontal axis, probabilities on the vertical axis. So with something like this, you would have attached a bar, with a dot that goes straight across. So if I had to draw the general shape of this graph, it would have been a horizontal line right across 1/6. That is called a uniform distribution because it is uniform. It's all exactly the same. Everything has an equal probability of occurring. Okay? A very boring distribution, not much statistical analysis. So you need to know what it is. Are we going to analyze it? No, there's nothing to analyze. It's very straightforward. Okay? On a different note is something called a normal distribution. And a normal distribution, we talked about a little bit in 4.1, is this one that looks a little bit like a bell, okay, or a mound shape. So it's sometimes referred to as a mound-shaped distribution. It's sometimes referred to as a bell-shaped distribution. And its main determining factor is that its mean, its median, and its mode are all the same. Okay, if you notice in terms of a frequency idea, this is the most frequent point, right? Because it's the highest on here, okay? So that is the mode, the one that occurs most frequently. That's from chapter 3. Its mean is the average. Well, there's a bunch of low values, there's a bunch of high values. So this middle value happens to be the median, obviously right split in the middle. It also happens to be the mean. It also happens to be the mode. The closer we can get to achieving this exact distribution, the more value we can draw from that information. Okay, and this is the gold standard of academics. And I talked about that a little bit in 4.1. A lot of academic institutions that are built on money, okay? So we're not talking about high schools. High schools are not built on money, okay? High school, we don't care. Whether you pass or whether you fail has no impact on whether I'm going to make money or whether the school is going to make money. We're funded by the government. But a university is completely funded by the students who attend it and pay for it. So there's a happy little spot that they want to be at. They do not want everyone getting 95%, 100%. Then their institution doesn't seem to have much merit. If everyone can go to that university and get very high marks, then it doesn't seem like an institution that people would hold in high regard. They want it to be difficult. If you're looking at some of the bigger universities in the world or the bigger universities in Canada, they're more difficult to get into. And they're looking for a quality of student that is rare, I guess. So you're happy to have a couple people getting really high marks, but you don't want too many. So that's why this frequency is very low. You also do not want people with marks very, very low. So imagine these are marks anywhere from, 100 way up here, all the way down to, say, 40%. Okay, well, if you need to maintain a C average or something, then they want, something around 60 here to be the people that pass the course. So they're okay giving up a few people over here, but they don't want to give up too many. Why do they not want to give up too many? Well, they want to hold a high standard, of course, but they also want to draw money. If you start failing too many courses and then you get kicked out of the program, that means you're no longer going to be paying tuition. Okay, tuition is funding their research, is funding their payment of professors. So they want to keep, once they get you to the university, they want to keep you at the university. So they're happy to have most people kind of sit in the middle here of this mound shape. They're like, we'll lose the people that really we don't want to be associated with our school anyway. The people that really are failing. Okay? The majority of the people we're happy to keep right in the middle, you know, a B average type student. And we're happy to have a few getting really good marks, but we don't want to have too many. So they are pushing towards a normal distribution. Now, a lot of the times a normal distribution doesn't occur. Maybe a professor misjudged and gave a really difficult exam and a ton of people ended up way over here in the failing. Well, they start adjusting your data and pushing you so that the people that were way over here get pushed towards what we would consider the high point here of the bell curve. Okay, so there might have been something called a skewed distribution. It looked a little bit normal, but there were too many people failing. They're going to push them to the right to make it look more normal. Okay, we're going to get into that a little bit more in the coming days, but the idea here is a normal distribution peaks everyone in all three measures of central tendency right at the same point, and that's the goal. Okay, if it looks a little bit normal, this still looks like a bell, this still looks like that mound shaped, but what's happening here is there's a tail, what we call a tail, that's leaning in one direction. So if the tail is leaning to the right, okay, obviously this is to the right, we consider it a positive skew or a right skewed distribution. Both of those words you have to know interchangeably. Okay, a positive skew or a right skew. And think it's moving in the positive direction on this horizontal axis. If the tail is more going towards the left, it's considered a negative or a left skew. And what happens is once you skew the normal distribution slightly, you separate the mean, median, and mode. The mode continues to be the high point. It goes wherever the mound goes, okay? But the middle point is moving as you pull it in either direction, okay? And the average is moving as you pull it in either direction. If you put a whole bunch of high values in or a whole bunch of low values, those are going to affect the mean, okay? So all of a sudden your normal distribution isn't so perfect where your measures of central tendency are all in the middle, okay? There's quite a bit of difference. So this occurs quite often. We do analysis within these types of distributions, but they're not optimal. So you should be able to identify what a right skewed normal distribution looks like and what a left skewed normal distribution looks like, and what it means in terms of, you know, sometimes the median and the mean are going to switch locations. It really depends on what it looks like, but what you need to know is it's not where the mode is. Okay, they're all in different spots. Okay, another one that's sort of on the same blend. This looks a little bit like a normal distribution except for it has two mounds. This is called bimodal. So again, the word bi meaning two. Okay, it just means it has two modes. There are two values that are most frequent. So maybe on a test we have a bunch of kids that get 80% and a bunch of kids that get 60%. Not very many near 100, not very many near 40. Okay, there's a couple sitting here at 70 in the middle. Okay, so 70 ends up being the median mark, 70 ends up being the mean mark, but 60 and 80 end up being the mode. Okay, so in something like this, two of them stayed together, the median and the mean both stayed in the middle. It's a symmetrical distribution, but the modes ended up going on either side of it. Okay, so that's referred to as bimodal. That's pretty easy to understand. The last one, and you should know this one from grade 11, is called an exponential distribution. And it's going one of two ways. It can be a positively exponential. This is called an increasing function. Or it could go in the other direction, which is this way, which is a decreasing function. And in either case, the mode, the median, and the mean are all messed up. The mode ends up being your high point, wherever it goes to, way at the end. The median is wherever you are in the middle here. I guess I should have put the median closer over here. And the mean is going to be the average again. So it's just another kind of messed up distribution. This one, there are quite a few statistical measures based on different types of exponential distributions. Not a ton we're going to get into this year. But just knowing the general shape. If I asked you a multiple choice question, I gave you these four graphs and I said, which one is bimodal? Could you point to it? That's really what you need to know from this. Okay. Normal, right skewed, left skewed, I would say are the most important understanding of the uniform for sure. And this is the one we're going to focus on. So from this point forward, from 4.2 until the end of 4.5, all we are dealing with is a normal distribution. Okay, so let's get started with what that means in terms of what's happening. And if you got ahead and tried to read the note, you may be confused until you get an explanation of what a normal distribution really is showing us. So there is a question in the notes that makes you graph something. I've graphed it for you. It sort of looks like this, and it shows some data against your age and the percent of women. What is this? The percent of women in each age group. So in general, there's 51.1% of the world is women. How many are in each age group? It looks like the highlights are somewhere between 30 and 50 is most of the women. So when you actually graphed it, it sort of had the mound shape, it had the hump shape. You know it's some sort of normal distribution, but it's skewed slightly. But it's just the idea of showing you how you would actually graph this data and get it. Okay, so you can take a look at that yourself. The main thing I want to do, and this is going to be the most important slide that we have. Perfectly normal distribution. And this is the thing, perfectly normal distribution. So the way that we write this down is sort of that in a perfectly normal distribution, first of all, some things that you might see in the textbook is that X is a random variable that belongs to a normal distribution with a specific mean and a specific variance. Now remember, we know what standard deviation is. It's just sigma. Mean was X bar. So this is sort of notation you may need to know. Coming up, not exactly today yet. Now, a perfectly normal distribution is going to look like this. Okay? Now, what makes it perfectly normal is the fact that the mean, the median, and the mode are all in the exact same place. Okay, so we know that right here, this is the mean, it's also the median, it's also the mode. That's what makes it perfectly normal. Now, we're going to use the symbol that we have been using for mean right here to represent it. We don't care so much right now about median and mode. We'll get to those eventually, but right now we're looking at how this is going to affect the mean. So the mean is directly in the middle. Okay, now we already mentioned variance, standard deviation having something to do with this. So standard deviation, if you remember from chapter 3, the definition of that, it's basically saying how close it is centered around the mean. So basically we want a standard deviation that's not too far from the mean. So imagine I said our class average is 75 with a standard deviation of 3. Okay, that means that within 3% of 75, so either above up to 78 or below down to 72, that's where a lot of people's marks are going to be. Okay, and the way that it's based is on a normal distribution. So what we're going to do is draw a line here and draw a line here. And this is going to be the idea that I am one standard deviation above the mean. Here, I am one standard deviation below the mean. Okay? And if you notice, in terms of this whole graph here, if you had to find the area under this curve, okay, so we're looking at all this area, what makes this perfectly normal is the fact that 68% of all the data is under this curve. I just started pouring rain here. Pouring rain, hail. You probably noticed it got dark. I have a light on, but it's getting dark. So 68% of the data is within one standard deviation. And if you had to find the area under this curve, this would make up almost 70% of the area under this curve. So that's the first idea. The next is if I draw another bar of equal width. Okay, so this width would have to be the same as this. All these are the same. If this width was within one standard deviation of the mean, this one is going to be within 2 standard deviations of the mean. Okay, so let me do that in a different color. So this here is going to be X bar plus 2 standard deviations. This one here is going to be X bar minus 2 standard deviations. Okay? And now to go right across, you came outside in the storm? You want to come say hi? Morgan, it's literally...
I know.
Come here. You don't even have a coat on.
I know.
Okay, come say hi. You didn't brush your hair.
Hi.
Hi. I haven't seen you in a while on a video. Okay, you going to do some art or something? You're going to sit there. Okay, so within 2 standard deviations, what the rule is here is that now 95% of the data is within 2 standard deviations. There's a blanket up there. Okay, are within 2 standard deviations. Now, what does that mean in terms of us? Now, if we look, we already accounted for 68%. So if we take this 95 that's under this whole thing and subtract 68, we get 27%. What? It's my second one. Okay, so this means that we already accounted for 68% here, which means 27 has to fit in these two. If we take 27% and divide by 2, we get 13.5%. So that means in each of these sections is 13.5% of the data.
Ben's yelling, Mama.
Go see what he wants. Okay, it's 13.5% of the data.
Wait, no, that's not Ben. That's somebody else.
Okay? Now, the very next line we have to draw, and the very last line that we're going to draw, over here, same equal distance, is the idea that this third bar is now within 3 standard deviations on either side. Okay, so it's either 3 above or 3 below. And now this, hold on, Lauren, is going to account for what we call 99.7% of the data is going to fall here. Notice there's only these little wings left on either side of the normal distribution. Okay, but almost 100% of the data lies under here. Now, if we've already accounted for 95%, and we want to find out what's in each of these sections, we take our 99.7, we subtract 95, and we get 4.7%. So we have to split this. Can you stop it, please? What? What? No, it wasn't a snowstorm ranking. Okay, so 4.7% has to fit into each of these two. Divide by 2, that gives me 2.35%. Okay, so in here, 2.35% fits. In here, 2.35% fits. Okay, so what's left over for the very last section is just, we had 99.7, there's 0.3% left. Divide that by 2. That means in this little part, there's 0.15%. In this little point, there's 0.15%. Okay, also of note, up here in this general area, was if there's 68% right across, in each of these halves, if you take 68% and you divide by 2, in each of those halves is 34%. Okay, so this is really what we refer to as the 68, 95, 99.7% rule. Okay, and you're probably saying, what on earth are you doing? Okay, what on earth am I doing? My daughter left probably, so I got mad at her. Well, we're splitting it up so that we can analyze the data based on our knowledge of a mean and a standard deviation. So this is all in theory based on the fact that we will have some numerical information. But you need to remember these numbers, 68, 99, 99.7. Once you know those numbers, you can start looking at each band and figuring out what that all means. Okay, this is fully written very nicely right here for you, which will help be explained. It'll all start to make sense once we start doing examples. Okay, so we will go right on. We'll do both of the examples. There's example 3 and there's example 4. And when we do those examples, this will make complete sense. Okay. So the first one says, use a normal distribution. There is supposed to be 50 grams in each package of cosmetic powder, whatever that is. I don't know. So it says here, use normal distribution to model this problem. The mean is 50.5. Now they use mu, but really x bar is the same thing. 50.5 is the average amount in each pack, 50.5 grams, with a standard deviation of 0.6 grams. Okay, manufacturers want to ensure each package contains at least 49.9 grams. What percentage do not is what they're asking us. So we're trying to find the probability that X is less than 49.9. Okay, so basically they average 50.5 grams, but if they're less than 49.9, they don't want to send them out to the market. So think of, this is about something called cosmetic powder. Who even knows what that means? But think about like a bag of chips. If you get a bag of chips, it tells you, 300 grams of chips. Now, every single bag doesn't have exactly 300 grams. It'll be a little above or a little below, but there'll be a threshold at which they can sell them. They can't give you 200 when they say 300, but they might be able to give you 290. Okay, there'll be some sort of threshold. So this is what we're trying to find. So right now you're going to be looking at this question being like, what the heck is going on? Well, they said model a normal distribution, okay? So a normal distribution where our mean is 50.5 and our standard deviation is 0.6. Remember, this had a variance here. So we always talk about this. X belongs to a normal distribution with a mean and a variance. So what you basically want to do in all of these questions is to graph it. Okay, graphing it allows us to figure out the answer at this point. Okay, there's going to be a lot of different methods we use for a normal distribution, but right now we're just going to use that chart that we made. So within the chart, what we want to do is draw the line down the middle and put the mean right there, 50.5. Remember, that's our X bar. And then we always want to go 3 above and 3 below. If you look at the original one that we drew on the last board, we went 3 standard deviations above, 3 below. And you're always going to go plus or minus 3. So what you have to do is look at this and say, well, if I'm going to go 0.6 grams above, then 0.6 grams above that, then 0.6 grams above that, then I'm going to have to use a little bit of math. Okay, you're going to have to add. So this is the mean, X bar. Maybe I'll just show you what this would have been, X bar. The next one is X bar plus sigma. So I take my 50.5 and I add 0.6. So now I get 51.1. On the other side, I take my X bar and I subtract 1. So I get 49.9. Notice this number's already popped up, and that's what you want. Okay, so we do that first. Then we go to the next line and we say, well, this one would be X bar plus 2 sigmas. So I'm going to add the standard deviation again. So 51.1 plus 0.6 is 51.7. If I subtract it, I get 49.3. Remember, this is X bar minus 2. And then the last one we have over here is when you're adding the third standard deviation or subtracting the third standard deviation. Okay, so you now add another 0.6 to this, and we get 52.3, and you subtract 0.6 again, and you get 48.7. So basically what they're saying, based on whatever cosmetic powder is, remember the rules. Within 68% of all the cases of cosmetic powder that are made, 68%, that middle section, will be between 49.9 and 51.1 grams. 95% of them will be within 49.3 grams and 51.7 grams. 99.7% of them are between 48.7 grams and 52.3. 0.15% are above 52.3, 0.15% are below 48.7. Okay, you could answer all kinds of questions about where it lies. They ask us one question. What percentage, okay, what probability is it that they are less than 49.9? So we take this area here and we're saying less than 49.9 would be anything that falls in these sections. Okay, all of this is greater than 49.9, less than 49.9. So you go back to that chart and you say, well, how much was in each of these sections? Well, if you refer back, you'll remember this one is 13.5% in that section. In this section is 2.35%. And in this little baby section is 0.15%. So if I'm looking, I need to add those numbers, 13.5 plus 2.35 plus 0.15, and I get 16% of all cases of cosmetic powder have less than 49.9 grams. So this company would not be able to sell those. 16% is a huge number. Okay, what do they do with them? Throw them out? I have no idea. Okay, so they'd want to adjust that to make sure it's more consistent. Okay, and that was the whole idea. The definition of standard deviation was that the smaller the number is, the more consistent it is. The smaller the ranges between these, the more consistent it's going to be. Okay? So this is the basis of all of these questions. You have to, every single time, draw this curve, put the mean in, add 3 standard deviations, subtract 3 standard deviations, check the percentages. Believe me, these percentages will show up in your brain. You're not going to forget them. 68, 95, 99.7, split them up. You'll be able to figure it out, no problem. Okay, so that was example 3. Okay, example 4 is now a similar idea, but we're going to have to draw it slightly different. There are actually 3 questions that go with example 4, A, B, and C, that can all be based on the same diagram, basically. So let's see what it's all about. Okay, so example 4 says, let X be the length of fish. They have a mean length. Why did I put a 1 there? A mean length, X bar, of 20 centimeters and a standard deviation of 2 centimeters. Okay, find the probability of fish population that's within these numbers. So if you had to draw this, and this is where it gets easier because now we're using nice numbers. Mean goes right in the middle, 20. Maybe you don't want to put the units. Within 1 standard deviation, okay, you add when you go to the right, you subtract when you go to the left. Within 2 standard deviations, add another, subtract another, and then the last one, then 3 standard deviations. We're up to 26, we're down to 14. Okay, so this is what this would look like. If you were looking at this curve, make the tail go a little bit further to make it look accurate. Okay, and again, if this is a truly normal distribution with a mean of 20 and a standard deviation, remember we write that 2 squared, then this is what it would look like. The questions they have asked are the following. Find the probability that's less than or equal to 22. Find the probability that it's greater than 16 centimeters. And find the probability that it is between 16 and 24. So you're going to look at all of those scenarios. The probability is less than 22. Less than 22 covers everything across here. So you simply look at all the sections. Well, what was this section? 34. This section, 34. This section, 13.5. This one, 2.35. This one, 0.15. Those are all percentages. So if you add all of those up, 34 plus 34 plus 13.5, 2.35 plus 0.15. I add all those up. I get 84% of all fish that are caught in this lake, wherever you are less than 22 centimeters. Okay, that makes sense because the average is 20. So obviously a large portion of them are going to be less than or equal to 22. How many are greater than 16? Well, greater than 16 means we have to look at this whole section. Greater than 16 means we go here and go all the way here. This is almost 100%. We're just missing these 2 little sections. Greater than 16. So if all the data lies under the curve, which it does in a normal distribution, 100% of the data lies under, we're just subtracting out the 2 parts that aren't part of greater than 16. So we're just going to subtract out these 2 areas, right? Everything else is greater than 16. So we're going to subtract out 2.35% and subtract out 0.15%, and then we get 97.5% of the data is greater than 16. So it's just analyzing this graph and picking off the numbers. Okay, between 16 and 24, well, between 16 and 24 is exactly within 2 standard deviations on either side. And this is the part of the rule that says 68 within 1 standard deviation, 95 within 2, 99.7 within 3. So you can add 13.5, 34, 34, 13.5, or you can just recognize that's 2 standard deviations and know that the answer associated with that has to be 95%. Okay, the textbook is terrible at doing this specific section. So you'll notice there's a couple textbook questions assigned. Page 419, number 1 to 4, which is more just talking about the distribution types, skewed and normal and uniform. page 30, 430 is just one A and B. And then I've attached 2 worksheets that deal more with this idea of the 68, 95, 99.7% rule, which is really what this is all about. Okay, so you'll practice those before we get into what would be considered the more difficult concepts associated with normal distributions. Because what's going to happen is, what if it doesn't lie exactly on one of the standard deviation lines? How do we figure out those percentages? So that's where we're going with 4.3, but that's not going to be till next Monday. I feel kind of bad that I got mad at Morgan. Oh, trials of working at home. Okay.